Welcome back to chemistry class. Today we'll study inductive effect. This is also one of the topic in the very first chapter of your syllabus, structure and bonding. Inductive effect. Inductive effect, the polarization of sigma bond. Sigma bond is the keyword. Due to electron withdrawing or electron donating effect of adjacent groups or atoms is known as inductive effect. A sigma bond between two atoms which differ in the electronegativity is polarized due to displacement of bond pair towards the more electronegative atom. Here, this is the sigma bond between two atoms which differ in electronegativity. This is carbon, this is a halogen atom which differ in the electronegativity. So, due to electronegativity difference, it attracts the electrons towards itself. So, polarization is due to displacement of bond pair towards the more electronegative atom. In this process, the electronegative atom gets partial negative charge while the other atom gets partial positive charge. Due to displacement of bond pair, the more electronegative atom gets partial negative charge and the other carbon atom acquires a partial positive charge. The induced polarity is transmitted through the sigma bond in the molecule by creating a permanent dipole. This carbon atom, which is now has a partial positive charge, attracts electrons from the adjacent carbon. It also acquires positive charge because the bond pair is displaced more towards this carbon, but the partial positive charge developed here is lesser than the previous one. This effect is transmitted through the carbon chain, and it is represented by arrow pointing towards the more electronegative atom carrying partial negative charge. It is represented by this arrow which is pointing towards the more electronegative element. The polarization is transmitted through sigma bond. This sigma bond, this sigma bond, this sigma bond, this sigma bond by creating a permanent dipole in the molecule. This polarization fades away from left to right as we move from left to right. Let us take the example of butyl chloride. In butyl chloride, this is the CCl bond. CCl bond in butyl chloride is polarized due to electronegativity difference. The electrons are withdrawn by the chlorine atom. The chlorine atom withdraws electron. Thus, the first carbon acquires a slight positive charge. A partial positive charge is acquired by the first carbon. In turn, it attracts electrons from the adjacent carbon atom, and it also develops a partial positive charge. And this way will continue further is how inductive effect is transmitted through the carbon chain. One must note that the inductive effect weakens away along the chain. As you can see, as we are moving away from the chain, from the electronegative atom, the positive charge is fading. This is positive, partial positive, this is less positive, this is less positive, this is less positive. So as we are moving away from the electronegative atom, the positive charge, the inductive effect is weakening and is not that much significant beyond the third carbon atom. Let us study the salient features of inductive effect. It arises due to electronegativity difference between two atoms forming a sigma bond. It is transmitted through the sigma bonds. No pi bonds are involved. The magnitude of inductive effect decreases while moving away from the group causing it. It is a permanent effect. It may create permanent dipole in the molecule. In general, inductive effect is relatively weak and is overshadowed by other electronic effects like resonance effect, hyperconjugation, etc. It influences the chemical and the physical properties of the compound. Types of inductive effect: depending upon the electron withdrawing and electron releasing nature of the atom or the group. Inductive effect is of two types: negative inductive effect, minus I effect, and the positive inductive effect or the plus I effect. The minus I effect or the negative inductive effect is due to the electron withdrawing nature of the group of atoms, and it is also called the negative inductive effect. It is represented by minus I. Following are the examples of groups in the decreasing order of minus I effect. This we have summarized and you can go through them. These are the groups. NH3 positive has the maximum minus I effect. COOH group has lesser one compared to NH3 positive. Halogens have less inductive minus I effect than COH. This is the CCl bond. Chlorine, it drags electrons toward itself, acquires partial negative charge. This one partial positive charge. It further drags from the second carbon. It also develops but partial positive but a lesser charge. It drags from the third one. This way it continues. So if it is a minus I effect, the negative inductive effect, if you see closely, the group attached acquires the negative charge and the carbon chain acquires the partial positive charge. But in the positive inductive effect, plus I effect, which is due to electron releasing nature of the group of atoms and donated by plus I, the carbon chain acquires a negative charge. This is the decreasing order of plus I effect. Tertiary butyl group CH3 whole thrice C greater than isobutyl CH3 whole isopropyl CH3 whole twice CH. CH2 CH3 has lesser, methyl has lesser, and hydrogen has the least. So this is the decreasing order. There are three methyl groups which are electron releasing groups. There are two methyl groups which are electron releasing. Here is only one, here is only hydrogen, and this is only hydrogen. So suppose this is the methyl group, this we have considered as a substituent. As a substituent, it releases electron. This carbon acquires a partial negative charge. It will require a partial positive because it is donating electrons. It is losing electrons. It will acquire a partial negative charge. In turn, it will drag electron towards the second carbon. This will also acquire partial negative charge but a lesser, and will continue through the chain. So you must make a difference that in minus I effect, negative I effect, the carbon chain acquires a partial positive charge, whereas in the plus I effect, the positive inductive effect, the carbon chain acquires a negative charge, partial negative charge. Now let us see why alkyl groups show the positive inductive effect. Practically, CH bond is considered as non-polar. There is partial positive charge on hydrogen atom and a partial negative charge on carbon atom. Therefore, if we compare, although it is non-polar, but if we compare very small values of carbon difference in electronegativity of carbon and hydrogen is more electropositive than carbon. So hydrogen acquires a partial positive charge, very slight positive charge, and carbon acquires a slight negative charge. So there are hydrogen atom acts as an electron donating group. Each hydrogen atom acts as an electron donating group. This cumulative donation turns alkyl group into an electron donating group. It donates electron towards carbon, and carbon acquires negative charge, partial negative charge, which it donates. So Alkyl group, the methyl group, is a electron donating group. Now let us move on to the applications of inductive effect. A very important application is the acidic strength of carboxylic acid. Acidic strength of carboxylic acid. Carboxylic acids are RCOOH group. RCOH group, how it acts as acid? It gives H positive ion. Acids are proton donors, H positive, and forms RCOO negative. RCOO negative, the carboxylate ion. The carboxylate ion are the conjugate base. A protonic acid is always in equilibrium with its conjugate base. Protonic acid is RCOH. Its conjugate base is RCOO negative. How it is formed? By the loss of H positive. Any factor that stabilizes the negatively charged conjugate base RCOO negative favors greater ionization of acid, that is, increases the acid strength. And an electron withdrawing group showing negative inductive effect, minus I effect. Minus I effect, what does it do? It reduces the negative charge on the conjugate base, RCO negative, the carboxylate ion, by pulling electron density and thus stabilizing it. Hence, the acidic strength increases when minus I groups are present. While plus I group decreases the acid strength as they destabilizes the conjugate base of the acid. Conjugate base of the acid is RCO negative, and more electrons are pushed onto it. So it was already negatively charged. It requires more of electrons, so it gets destabilized by releasing electron density, which in turn increases the negative charge on the anion and thus destabilizing it. So minus I effect, how minus I effect and plus I effect affects the acid strength. Let us see that. First we will study the acid strength due to the minus I effect group. Acid strength increases with the strength of the minus I effect group attached at the alpha carbon of the carboxylic acid. If at the alpha carbon atom a group is attached which has a greater minus I effect strength, then it will increase the acid strength. For example, let us take the example of acetic acid. Acetic acid is CH3COOH. This is the alpha carbon. At the alpha carbon atom, suppose one of the hydrogen is replaced by chlorine, then it will be a chloroacetic acid. If it is replaced by fluorine, it is fluoroacetic acid, NO2 nitroacetic acid. So if we compare nitro, fluoro, chlorine and here a hydrogen, we see that nitro group has the highest minus I effect, then followed by fluorine, followed by chlorine, and then the methyl. So this nitroacetic acid has the maximum acid strength, followed by fluoroacetic acid, followed by chloroacetic acid, and finally acetic acid is least acid. That is, acid strength increase with the increasing number of minus I effect group. Now this was the strength of I effect group, group causing minus I effect. This is number of minus I effect group. Like in acetic acid, we take monochloroacetic acid, dichloroacetic acid, trichloroacetic acid. These examples differ in the number of chlorine atoms attached at the alpha carbon atom. As the number of chlorine atoms at the alpha carbon atom increase, the acid strength increase. So trichloroacetic acid has the 3 chlorine atoms, so is most acidic, followed by dichloroacetic acid having 2 chlorine atoms, then one monochloroacetic acid having one chlorine, and finally acetic acid is least acidic. So as the number of minus I effect group, electron withdrawing group increases, the acid strength increases. Here, as the strength of minus I effect group increases, group causing minus ion effect increases, the acid strength increases. The third one is the position of the substituent exerting minus I effect. Here the substituent is at alpha position. Here the substituent is at beta position. Here the substituent causing minus I effect is at the gamma position. This is acetic acid, and this is butyric acid. This is COH group. Carbon adjacent to COH group is alpha. Adjacent to alpha is beta. Next to beta is gamma. So here it is at the alpha. It is alpha butyric acid. This is beta. This is gamma. So closer the substituent causing minus effect to the carboxylic acid group, greater will be the acid strength. Here it is. So this one is most acidic, followed by beta chlorobutyric acid, followed by gamma chlorobutyric acid. So as the distance between the chlorine atom and carboxylic acid group increases, the acid strength decreases. All these three examples, the strength of minus I effect group, number of minus I effect group, and the position of minus I effect group, these can be explained due to the electron density between OH bond of carboxylic acid decreases due to minus I effect. Electron density decreases, thus H positive ion can easily be released and the stability of carboxylate ion increases. As the stability of carboxylate ion increases, the acid strength will increase. How the plus I effect affects the acid strength. As the plus I effect decreases the acid strength, the reverse of minus I effect. Minus I effect was increasing the acid strength, but the plus I effect decreases the acid strength. And the reason is just the reverse of it. The plus I effect, minus I effect here is increasing the is decreasing the electron density, but plus I effect will increase the electron density. Here it is to carboxylic acid group is attached hydrogen, here methyl, here ethyl, and here isopropyl and tertiary butyl. So hydrogen has the least plus I effect, so it is most acidic. Methyl group has comparatively less plus I effect, so is less acidic. Here are ethyl group, it has greater plus I effect, so the acid strength further decreases. Here it is two methyl groups having a greater plus I effect, so it will decrease the acid strength, and in this there are three methyl groups exerting plus I effect, so acid strength decreases. So the greater the number of plus I effect, lesser will be the acid strength. Similarly, formic acid and benzoic acid, formic is better. You can go through these examples. Alcohols, the same strength, the same order. The above orders can be explained on the fact that due to plus I effect, electron density increases between OH group. Plus I effect will force electrons towards the OH bond, increases between OH bond of carboxylic acid or hydroxyl group. Thus hydrogen ion is not easily released or the acid strength decreases. So plus I effect, what does it do? electron density is increased. Due to plus I effect, electron density is increased between the OH. Due to minus I effect, electron density is decreased. And due to plus I effect, electron density increases between OH bond of carboxylic acid, and the release of H positive is made difficult. And the acid strength decreases. The next application is the strength of bases. Strength of bases. Base is a compound which releases lone pair of electron according to Lewis. This is the Lewis concept, and accepts H positive ions. The strength of base increase due to plus I effect and decrease due to minus I effect. The plus I effect will increase the lone pair of electron density. So it will increase the base strength. Minus I effect will decrease the electron density, and due to decrease in electron density, basic strength will decrease. For example, ammonia is a base. It is a weaker base than alkylamines. Dimethylamine, methylamine, ammonia and chloramine. Dimethylamine, there are two methyl groups. These two methyl groups will push electron towards nitrogen. The electron density of nitrogen increase. Electron density increase. Now it can easily give lone pairs of electrons. So it is basic. Here in methylamine there is only one methyl group which will push electron towards nitrogen. So electron density will increase. Now it can donate lone pair of electron. It is basic, but less basic than this dimethylamine. Ammonia, it has no electron releasing group like methyl, only hydrogen are there. So lone pair can be released easily, and it is less basic. In chloramine, chlorine is minus I effect. It draws electron toward itself. The lone pair of electron or the electron density at nitrogen decreases. So it has the least basic strength. But it is important to note here that trimethylamine has three methyl groups. So three methyl groups can increase electron density too much on nitrogen. So it should be the strongest base. Trimethylamine is not a stronger base than dimethylamine. This exception, trimethylamine is not stronger base. Dimethylamine is a stronger base than trimethylamine. This is due to two reasons. One is the steric effect, other is less solvation. The three bulky methyl groups repel each other. The three bulky methyl groups, steric effect is the bulky groups repel each other, and due to this repulsion they are unable to release electron towards nitrogen. And less solvation. Solvation is the association with solvent molecules, and due to less solvation, the base strength further decreases. The base strength is good when the solvation is high. Thus the order of basic strength is dimethylamine greater than methylamine greater than trimethylamine. So trimethylamine, the base strength is less than methylamine and dimethylamine, but is greater than ammonia. Reactivity of next application is the reactivity of alkyl halide. Alkyl halides are more reactive than the corresponding alkenes due to the polarity of CX bond. The reactivity increases with increasing plus I effect, which is as follows: tertiary greater than secondary greater than primary. The order of reactivity of alkyl halides is this. This is the polarity of CX bond. The alkyl halides generally undergoes nucleophilic substitution reactions. So nucleophilic towards the nucleophilic substitution reaction, they are SN1 and SN2 reactions. This tertiary in SN1 reactions, due to the increased polarity of CX bond, this halogen can be easily released and the carbonium ion is more stabilized, so its reactivity is highest. In the secondary also, the carbonium ion formed by the release of X positive can be stabilized. So this is the reactivity towards the SN1 reaction. The next is the dipole moment. The next application of inductive effect is the dipole moment. The greater the minus I effect, the more will be the dipole moment of the molecule. For example, order of dipole moment is CH3F greater than CH3Cl, CH3Br greater than CH3I. Dipole moment, you all know that it is represented by mu, and it is the equal to the charge divided by charge multiplied by the distance between the two. So greater the electronegativity or the minus I effect, greater will be the polarity or the charge developed. So CH3F is has the highest dipole moment compared to CH3I. Because of the minus I effect of fluorine, the polarity of CF bond is maximum. And this is the order of minus I effect. Fluorine greater than chlorine, greater than bromine, greater than iodine. Next application is the reactivity of the carbonyl compounds. Carbonyl compounds are CO. The plus I effect group increases the electron density of the carbonyl carbon. Hence, the reactivity towards nucleophiles increases. Thus, formaldehyde is more reactive than acetaldehyde and acetone. Formaldehyde, acetaldehyde and acetone. This CO bond, there are no electron releasing group. Here methyl is electron releasing group, or the plus I effect shows plus I effect. This will release electron towards carbon. So the polarity of this CO bond will decrease. As the polarity of this CO bond will decrease, reactivity towards nucleophile will also decrease. Here there are two methyl groups. They will, due to plus I effect, will release more electron towards carbon, and this will decrease the polarity of CO bond. And due to the decrease in polarity of CO bond, the reactivity towards nucleophile will decrease. So formaldehyde is more reactive than acetaldehyde, is more reactive than acetone. Because of here there are two groups showing plus I effect, there is only one group showing plus I. Next is the application is the stability of carbocation or carbonium ion. This we have discussed in hyperconjugation also. The stability of carbocation increases when plus I group like alkyl groups are present adjacent to the positively charged carbon atom. Earlier also in this video I have discussed that this is the carbonium ion, and the groups which are able to neutralize the charge, decrease the charge, will be more stable. Here there are three groups, three methyl groups which show plus I effect. They will repel electron towards, release electron towards carbonium ion, and the positive charge of carbonium ion will be discharged, and due to this neutralization it will get stability. Here there are two groups, plus I groups. This will decrease the electron density on the carbonium ion, so the stability will increase. Here there is only one, and there are no plus I effect group. So the greater number of plus I effect group attached to carbonium ion will decrease the electron density and increase the stability. The plus I group reduces the positive charge on carbon by donating negative charge density through positive inductive effect. This is the positive charge. This positive charge is reduced by the 3 methyl group. Here the positive charge is reduced by the 2 methyl group. This results in greater stability of carbocation, whereas minus I group destabilizes the carbocation. The minus I effect group will attract electron towards them and the positive charge will be further increased. So the stability will decrease. This is, you must note that any factor that increases the charge, either negative or positive, this is the positive charge. So the factor which will reduce the positive charge will increase the stability to an ion, results in destabilization, while any factor that reduces the charge results in the stabilization of that ion. This I have just now discussed. The next is the stability of free radical. The stability of free radicals is similar to those of carbonium ion. In carbonium ion there is positive charge, but in free radicals there is a single electron on each carbon atom. The stability of free radical increases with the increase in the number of alkyl groups or groups showing the plus I effect. Thus the stability of different radicals, tertiary greater than secondary, greater than primary, greater than methyl. This we have discussed in hyperconjugation also. Next is the stability of carbanium. Carbanium, it is just the reverse of carbonium, because here it is the negative charge. So the groups which will reduce the negative charge on the carbon atom will stabilize it. These are the three methyl groups. So these are plus I effect. The plus I effect will increase the electron density at the carbon atom. So when they increase the electron density, the negative charge, that will destabilize the carbon atom. In methyl group there is no such, so it is no electron releasing plus I effect, group showing plus I effect, so it is more stable compared to the ethyl, then more than the isopropyl, more than the tertiary butyl. So methyl, primary, secondary and tertiary. Now the order is reversed. The tertiary carbanium is least stable while the methyl carbanium is most stable. For this presentation I have consulted these books, and you can also go and study these topics in detail in these books. Thank you.